Hello, here we look at determinants of elementary matrices. And then using the relation between these matrices and elementary transformations, we will have an algorithm for computing determinant using elementary transformations. So let's recall the elementary matrices. There are three types, as many as elementary transformations: the row addition or column addition, depending on what side we are multiplying by in this matrix, and it is, as every elementary matrix, mostly identity, but with some perturbation, namely taking ith row, multiplying it by c, and adding to row number j, we will have this extra non-zero entry. The rest is zero. The determinant of such matrix is easy to compute just from the shape of it. It's lower triangular matrix. The determinant is 1. The determinant of the next type of elementary matrix responsible for row swap or column swap is the following. So let's recall the matrix again. It's the identity matrix, but we swap the row number I and number j. So the positions of ones change from the diagonal to off diagonal. The rest is just as in the identity matrix. If we follow the definition of the determinant and look at the expansion as a sum through permutations of products of matrix entries sitting in different rows and different columns, there will be only one such product corresponding to non-zero ones, because again, reading row by row, we have to take something non-zero, and there's only one choice each time, and then the permutation will be the corresponding permutation controlling the sign of this product with absolute value 1 will be the permutation which swaps I and j, namely a transposition between I and j. Its sign is -1, and so is the determinant. Finally, for the last elementary transformation of row scaling, we have the matrix which is 1 again everywhere on the diagonal apart from the ith row and ith column, where we have number c. That is even easier than before to compute. It's just a diagonal matrix. The determinant is c. So with this knowledge and with one important property of the determinants, namely multiplicativity, that for two square matrices, the determinant of their product is the same as the product of their determinants, we can now devise the algorithm. So multiplying by this matrix is any matrix, we perform elementary transformations. If we multiply with elementary matrices from the left, we do row transformations. From the right, will be column transforming. So let's again rewrite these statements for determinants in terms of elementary transformations. Imagine we have a matrix A, square matrix, with some generic entries, and then we do row transformation of row addition type. So we transform the row number, say j, and add to it so this is supposed to be ji sitting in jth row and ith column. Row number j with help of row number I, so we add elements of row I scaled by coefficient c to row j, and then the rest of the matrix is as it was originally. And the determinant will be just the same as the determinant of the unchanged matrix. The swap of rows performed by matrix multiplication with This type of matrices will cost, so swapping row j and row I in place of row I, now use row j and vice versa. Again, the rest is as an original matrix. Then it will be equal to the original determinant, but with a price of negative sign. And finally, when we do row scaling, we just pick a row, say ith, and then scale all entries with one coefficient c, in. Again, the rest is unchanged, and that can be rewritten as the matrix without any changes, scaled by coefficient c. So these are the rules which are easy to remember and easy to perform, and each of these rules is really performing an elementary transformation on that matrix and then seeing what is the relation between the original determinant and the new supposedly easier one. If we swap rows, we create a sign. If we do row or column addition, we don't do anything to the determinant. If we have a number, effectively divide by a number, if we transition from this side to this side, we scale c out of the row, and that just comes out of the determinant as the same scaling coefficient. So these are the moves of effectively Gauss algorithm for computing determinants. We start with matrix, and using elementary Gauss transformations, we can transform it to, say, upper triangular shape. And we'll have something on the diagonal. I'll call these diagonal entries T1, Dn. And I'm assuming that the matrix has as many pivots as columns or rows, so no free variables. Otherwise, we'll have just a line of zeros, and that is immediately giving us zero determinant answer. So that is a easy case and also interesting case. We're doing elementary transformations depending on the type. We have prices to pay, like a sign or a coefficient, which we take out of the matrix. So collecting them all in front, some number of them, depending on how many of these interesting transformations we do, we have these two determinants aligned. And finally, using the answer for the upper triangular shape determinant, we have complete answer. So whatever prices we paid doing the transformations times the product of diagonal entries is the answer for the determinant. So that is the algorithm which we can use computing determinants of any type of matrices, square of course, but zeros or not doesn't matter. We will always be there because Gauss elimination algorithm will always give us a row echelon form, and that effectively will be this upper triangular shape. Let's look at an example, something of size 3, but with arbitrarily bad entries. So something like that, 1 here, 2 here, then say 3 here, 4 in this corner, and then 5 placing it here, 6, 7, say 8, and 9. And yeah, that is a matrix which we should be able to bring down to a row echelon form using elementary transformations. And the first one is good for the first pivot, and the first move or two moves is to clear the first column below the pivot. That will be done by row subtractions, row say 2 minus 8, row 1, and at the same time row 3 minus 4 copies of row 1. Both of these transformations don't change determinants, so I'm just equating the before or after transformation determinants. And the transformation transforms the matrix to this shape, and then what happens in these entries is most interesting, so, or in these 4 entries rather. So in here we have 5 without 6 times 8. that should be negative 43. And in here we have 9 without 3 times 8, and that is negative 15. So this entry is 7 without 4 times 6. That should be negative 17. And finally, 2 without 4 times 3 should be negative 10. So that's the first pivotal column, good and all, and then we have to imagine a second pivot and make it happen. So that would be like taking 43 and scaling down to 1, but that will be creating denominators, which I would rather like to avoid, and instead I will just do something less canonical but still allowable. So I will be looking for my second pivot in this column number 3. And it is okay because I can swap columns as well as rows and place my pivot where I want it to be. These elementary transformations, which were again presented for the row case, can be done with columns with the same relation between before and after the transformation results. Because column transformations will correspond to multiplying with elementary matrices not from the left but from the right, but the rule will still be the same, relating determinants. And so I will be really making use of these two numbers being divisible by 5 with small fractions. So that will be with small ratios. So that will be really making the computation easier. So what I will do first, I will just subtract row 3 from row 2. Making, instead of negative 15, negative 5, which will be a divisor for the other number. So that will be creating, as I say, negative 5 here, and then negative, still negative, I believe 26. And then I can now use this 5 as my second pivot, effectively, and eliminate negative 10 with it. Again, using the row transformation of subtraction type. So that is not changing the determinant, not affecting the determinant. The same now with this row 3 minus twice row 2. The determinant is still the same. What I will have is 0 here, and the 0 is in here as well, and then I will have something like negative negative 43. No, it's not negative 43. So twice 26, twice 26 subtracted, making positive, then it will be 52, and 52 effectively without 17, right? That will be, I believe, 35 with positive sign. So that is the result of this transformation. Now I can move this into the second pivot position using column swap. Column 2 and column 3 changing positions will make it look like that. So the first column is unchanged, and 3, negative 5, 0 is now the second column. 6, negative 26, positive 35 is the last column. Column swap costs a negative sign. So finally, I'm ready to read off the determinant from this upper triangular shape. The determinant is a product of diagonal entries which is negative 5 times 35, which is negative 175, because of the negative sign in front of the determinant, I have positive answer 175. So that is a relatively quick way of computing the determinant of an ugly matrix, but it requires some arithmetic gymnastics, and that might be prone to mistakes. Unfortunately, there is no easy way of checking for the determinant answer like we have for solving linear systems or computing inverse matrices. We cannot substitute our solution into the system or check the matrix is the inverse by multiplying with the original one. But we can compute the determinant in another way using a different method, and then compare the answers, and if we can forget about this answer and do it more or less independently, and the comparison gives us the same answer, then it's a strong indication that computations are correct. So this time I will be just using the definition, using the formula. And the formula will involve 6 products of matrix entries sitting in different rows, in different columns. So the first such will be diagonal entries, 1 times 5 times 2, comes with some sign plus. The second will be again with sign plus, product of these 3, 6 and 9 and 4. One more with plus sign, 3 times 8 times 7, and that will exhaust all plus sign plus terms in the determinant. The rest will be with minus. Taking anti-diagonal product 3 and 5 and 4. Then I will have 6, 8 and 2. And the final one will be 1, 9 and 7. And the rest is arithmetic, so just multiplying, computing the products, and then computing the sum. So the first product is 10. The second product is 24 times 9, so it is 240 without 24. It has to be 216. This is, I don't know which one is better, 24 times 7, so it is 24 times 9 without 24 and without 24 again, so without 48. That has to be 168. This one is, yeah, more or less easy. It's like 3 times 20, it is 60. This is, I don't know, 12 times 8 is innocent enough. It's 96 with minus sign, and this is just from a multiplication table, negative 63. And then, yeah, making a balance. So these with that will be 123 out of 168. We will be having left 45. And these, so these terms are accounted for. This and that are taking a difference. It's 210 without 90, which is 120. Finally, summing the 3, we will have, so these two, 130, and then 45 on top, 175. Matching answers, good indication that computations were done correctly. So yeah, that's it for this elementary transformations method of computing determinants.